Hey there, so here's that extra practice video I promised from Thursday. Let's call Thursday March 5th? No, that's way too, no, 853, March 3rd. When I missed class on March 3rd, this is what I was going to talk about. Okay, so we're going to use the first derivative test to identify the extrema for each function. Remember 3.3 first derivative test. We're going to label each point as a minimum, a maximum, or a non-extrema. And we'll talk about whether it's absolute or relative. Evidently, this document is saved on my PC. There we go. Okay, first derivative test. So in order to do the first derivative test, we will find the derivative of g. Oh, I'm using a different board at home than I use in class. Here we go. 2x minus 4. Yeah, that's looking familiar. 2x minus 4. And we need to find our critical numbers first. Remember that we are looking for extrema. Extrema occur where the first derivative is 0 or does not exist. And we call those critical numbers. All right, critical numbers. We find those. 0 equals 2x minus 4. Add 4 to both sides. Divide by 2. We'll find that x equals 2. Remember, our critical numbers also divide up our intervals. So I'll have an interval from negative infinity to 2. And from 2 to infinity. I need a test point. TP, that's not toilet paper, that's a test point. Let's go with x equals 0, and I'm going to use x equals 5. Remember, anything bigger than 2 on the right, anything less than 2 on the left, and 0 is pretty awesome, so I'm going to use it. I'm going to find g prime evaluated at 0, and that will be a negative 4. I'll find g prime evaluated at 5, and that will be 10 minus 4, which is 6. Notice it goes from negative to positive. That's negative to positive, decreasing to increasing. Here we know a whole bunch. We know increasing on the interval from 2 to infinity. That's an ugly infinity, isn't it? We know the function is decreasing on the interval from negative infinity to 2. I like to be positive. Positive generally is increasing. I don't know why. Increasing because I like money coming in, not money going out. Okay, so I listed increasing first, but I should have listed in order of the interval. Our critical number, x equals 2, gives us a point, a y value, at the original function, all right, g of 2. I have an eraser here. There we go. Y equals g of 2, original function, we're looking at 2 squared minus 4 times 2 minus 320. It's quite the number. 4 minus 8 minus 320. This is negative 4 minus 320, which is minus the 324. So let's move this down a little bit. Let's see what's going on here. We have a minimum. Where we look is determined by the derivative. What the actual height is determined by the original function. This minimum is actually absolute because it's a quadratic. It's a quadratic facing up. We know that it'll never be more minimum ever lower than that. Oh my goodness. Okay, we got this. let's look at the cosine of, let me just move this while I have a minute. Cosine of 3x over 2. All right, we want to find minimum, maximum, all the critical numbers, what's going on with them. We start with the derivative. The derivative of cosine is minus sine of x. All right, so minus sine of inside, and then multiplied by the derivative of the inside. Right, we have a chain rule going on here, where we have the inside and we have the outside. So I will absolutely write this better. This is minus 3/2 sine of 3x over 2. Now when is this 0? We know that h prime of x equals 0 when the sine of 3x over 2 equals 0. We know in general, it's a different board than what I'm used to in class. My hand's cramping. I know, excuses, Tuesday, shut up in calculus. Okay, the derivative is 0 when sine is 0, right? Because negative 3/2 is never going to be 0, so the derivative can only be 0 if the variable part was 0. And we know that sine is 0 when x is equal to all multiples of pi for some integer n. Well, in general, this is in general. Oh my goodness, I don't even know how to say what I'm trying to say right, because somebody's got to listen to me talk here. I'm going to start listening. We know that the sine is equal to 0 in general at all the pi values, but this isn't an x in general. It's specifically 3x over 2, which is equal to the n pi. Multiply both sides by 2. 2 pi n for some reason, I don't know, divided by 3. These are all of the values where we're going to have some type of inflection. What is this going to look like? On a number line, all right, we're looking at, let's let n be 0. When n is 0, we're at 0. When n is 1, we're at 2 pi over 3. When n is 2, we're at 4 pi over 3. And similarly behind. All right, so we can make this number line go in both directions. And these are all little intervals. That's the problem. These are all little intervals for infinity because there's no domain restriction going on here at all. So let's see if we can generalize this. Okay. Between 0 and 2 pi over 3, okay, between 0 and a half is this, between 0 and 2/3 is this nice test point of pi over 2. So I can find the derivative at pi over 2. Let me see, that is minus 3/2 times the sine of 3 over 2, right? The 3 over 2, and then the x is pi over 2. Ugly, 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 that's a minus 3/2 sine of 3 pi over 4. And remember, we only care if it's positive or negative. Positive or negative because we're just looking for the sign. Is it positive or negative here? The derivative and sine of 3 pi over 4. This is in quadrant 2, and in quadrant 2, sine is positive. A positive number multiplied by a negative number gives us a negative result. And we know in this area, we will be decreasing. Now I want to pick any number between 2/3 and 1 1/3. I'm going to use a different color here because I can. Maybe here we're looking at pi. The derivative at pi is minus 3 halves sine of, now in place of the x, I want to put in a pi. So we'll have 3 pi over 2. I almost screwed that one up. Test point of pi. So we'll put pi in for x in our derivative. So 3 pi over 2. The sine of 3 pi over 2 is a negative 1. Negative 1 times a negative 3 halves is positive, and check that out. We found what looks like it's probably a pattern. We can check it down here and see if it truly is. Maybe we will check negative 2/3. How about a negative 1/2? We could check as many of these values if we need to in order to determine how this is going. So negative 3 halves sine. And this, right, is very similar to the pi over 2, only it's negative. This will be negative 3 pi over 4. But you see, the angle negative 3 pi over 4 is in quadrant 3. And in quadrant 3, the sine is negative. And a negative times a negative is surely positive. And yeah, knowing the nature of the graph of the cosine, we just figured this out without even thinking about phase shift or amplitude or all of those other things that we talk about in trigonometry, whose words escape me right now. So how would we write this answer? So it will be increasing. Okay, increasing. So that's the blue intervals. So I'm thinking to myself, negative 2 pi over 3 to 0, 2 pi over 3 to 4 pi over 3. And it continues in this pattern in both directions, decreasing. We're looking at 0 to 2 pi over 3. So it looks, wow, I don't even know how I would write this. Most likely we would have to have a restriction. We don't have to. There is a formulaic way of doing this. In general, increasing from wow. Nope, I can't do it. I'm recording this after the birthday party, after a long day, and it's not happening right now. I would use this as a maybe restricted domain on 0 to 2 pi specifically. I would then write down my increasing and decreasing from there. All right, but we can find some patterns in it, and there is a way of writing that. I'm just not coming up with it right now, and I'm totally comfortable in who I am to be able to admit that to you. Okay, so we're still using the first derivative test to identify the extrema for each function. The extrema are going to be at all of these points. All of them. Every 2n pi over 3 will have a critical value, and this critical value will all have the same height. And this height we find will actually be 1 all the time. All right, let's do a polynomial. Now, first thing is I look at this negative 5 times x cubed. I know that because it's x cubed, my n's finish different in behavior. And the minus tells me it's generally decreasing. So I know that this function, whatever's going on in the middle, there are no absolute max or mins. Okay, because we know the shape of this graph, we know there will not be any maximums, absolute maximums or minimums. Any of that we find must be relative. The first derivative is negative 15x squared plus 15. Of course it is. And when we set that equal to 0, I'm going to factor out a negative 15. Negative 15, when I take it out of negative 15x squared, I get just the x squared. But when I factor out the negative, it changes this to a minus. And, right, 15 divided by a negative 15 is a minus 1. This is nice because this allows us to solve x equals plus or minus 1 are our critical numbers. Remember, our critical numbers are how we divide up our interval. No, that's not right. It's how we divide up our interval. All right, we stop it at negative 1, and then we stop it at 1, and then we take it on forever. So we want test points. A test point over here, I'll use x equals negative 2. Remember, we can't use the endpoints of these intervals, so we need to choose something in between the values. And it could be anything. I'm just using 2s because I can't use 1s, and that's why. Purple. Value of f prime of x. So I'm going to, let me just separate these a little bit. I don't have the tables all lined out, but a little separation is nice here. F prime at negative 2. All right, let's put negative 2 in here. Negative 2 squared is positive 4. What in the heck? Oh, it's because my brain's not working. 4 times a negative 15 is negative 60. Negative 60 plus 15 is negative. We don't care that it's negative 45. We just care that it's negative, which tells us that our function is decreasing here. First derivative evaluated at 0. At 0 plus 15, so really we care that it's positive. It's increasing here. And if we use the test value of 2, we see that since we have it's an even function, right? It doesn't matter if we put in 2 or negative 2, we actually end up with the same answer because 2 squared is the same thing as negative 2 squared. So we'll have negative 60 plus 15, which is negative, and we have a decreasing section. So what's going on here? We know by the first derivative test, if it switches from negative to positive, we'll have a minimum. If it switches from positive to negative, we'll have a maximum. We've already determined that there's no absolute, so these must be relative, maximum, and minimum. I'm going to separate them here. That actually should go there. Relative. There we go. Minimum. Remember, the derivative tells us where to look. So we know that the minimum is at negative 1. Right? That's right in between. And the maximum is here at positive 1. And I wrote those in the wrong order. Of course, because I wasn't paying attention. Always pay attention. And always, 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 we get this from the original function. F of 1 is negative 5 times 1 cubed plus 15 times 1 plus 7. So that's negative 5 plus 15 gives me a negative 10. It gives me a positive 10. And 10 and 7 makes 17. Derivative tells us where. The original function tells us what the y value is. Same thing if we plug in the negative 1 into the original function. We have negative 5 times negative 1 cubed plus 15 times negative 1 plus 7. Now, this negative 1 cubed will be negative. Negative times the negative 5 makes a positive 5. But now I have a negative 15, so I have 5, and a negative 15 makes the negative 10, plus 7 leaves us with negative 3. Relative min and max, we have intervals of increasing and decreasing. We have all the information that we can glean from that first derivative for right now. Oh my goodness, how many more examples do we have? 3 more. I'm going to shut up and do some work. Let's do it. We take the derivative. Bring down the 1/3. Subtract 1, so that'll be a negative 2/3. Remember, the derivative of 7 is 0. I'll simplify anytime we're going to use it. We're not just finding it for derivative reasons, but we're going to use it. We are going to simplify. So this is 1 over 3, and that negative exponent. We take that x to the 2/3 to the denominator. Now, we know that f prime is never 0. Poor notation, but it's never 0 because the numerator can never be 0 because it's a 1. But f prime does not exist at x equals 0, right? 0 is in the domain of the original function, but it's not in the domain of the derivative. So what's going on at 0? Let's put it over here. We got plenty of room. All right, let's see what's happening at 0. So we have our intervals, negative infinity to 0 and 0 to infinity. We want a test point. Let's use test points of -1 and +1. And from there, we want to evaluate in the first derivative. So f prime at -1. Oh, that's positive. All right, the numerator is always positive. It's just a 1. The cube root of -1 is -1. If I square -1, I get 1. And I multiply that by 3, I get 1/3. So this is positive. But because of that squaring action going on there, right? The cube root of 1 is 1. 1 squared is 1. 1 times 3 is 3. Oh, this one's positive too. Increasing and then increasing, which tells us, according to the first derivative test, no sign change. So it's not an extrema. All right, end of story. It's not an extrema. It's a critical number. There's something cool going on at 0,7. 0. And when we evaluate, we know that's 7. But nothing of value. The graph just kind of looks like this. 7. I got to move it up a bit. Only this part is actually on the axis. All right, so there's some funky stuff going on, and this is kind of the opposite of what we saw with the x cubed portion of our graph today. I think we have an x to the 5th graph, and there was that flat spot where the 0 wasn't a critical number. It was a critical number. It was not a extrema. Whew, find the words. All right, we saw that in the lecture for 3.4 today. This is one of those exceptions where we have a vertical tangent line instead of a horizontal one. So it's significant because something weird's happening there, but it's not weird enough that we assign other terminology to it. All right, I only have 2 to go, so I'm going to throw this down on a different page. Let's see what the difference is when we have the shift now inside instead of outside. Remember, when we're looking for extrema, we always need critical numbers. Extrema will always happen at critical numbers. So we bring down the 2/3, leave the inside alone, subtract 1 from the exponent, and I'm going to write it because I'm a math professor, that's what we do. Don't forget the derivative of the inside. In this case, right, if you forget, it's no big deal, but when you start forgetting all the time, if you get used to ignoring it, it quickly gets left out when it matters. So that 2 stays in the numerator, that 3 is in the denominator, that negative exponent tells me we're looking at the cube root of x plus 3. All right. Now again, g prime of x is never 0 because the numerator is never 0. G prime of x does not exist at an x value of negative 3. Right? At negative 3, my denominator will be 0, and bad things happen when denominators are 0. So we have our number line. Negative 3 is our critical number. Something important's happening there. Let's see what type of important it is. Enunciation matters. Okay, some test points. Let's use x equals negative 5 and x equals 0. I'm going to throw down this little line here. Let's see if I can keep myself aligned. The derivative at negative 5. All right. Negative 5 plus 3 is negative 2. So that's 2 over 3 cube root of negative 2. Now here's the cool thing. Remember, we don't care what the number is. We know that numerator is always positive. And we know that the cube root of a negative number is negative. And a negative times 3 is negative. So regardless of what the digits are, we know this will be positive divided by negative, which results in negative, which is decreasing. Try our other test value, hoping this will be easier. This gives us 2 over 3 times the cube root. Oh, what is this? 0 plus 3. Cube root of a positive number is always positive. Positive number times 3 is positive. So we find a positive divided by a positive. And that's always going to be positive. And we're increasing. So we find that we actually do have a minimum here. Just because this value makes so the derivative does not exist, don't forget, that's still in the domain of the original function. So we saw one example where something funky happened with the derivative. There's no extrema. Here we find something funky happening with the derivative. There is an extrema. So you can't just automatically say, oh, cool, you know, it's a funky thing that's happening. And no, you actually have to work it out each time. So this is a global, based on what we know of cube root shape of a graph. This will be a, can't be. It is. Cube root and then square it. So a cube root would look like, nope, a cube root looks like this. And then when you square it, it looks probably like that. Not that. Yeah, a cube root and then square it, right? So everything's squared. It kind of, yeah, I think that's what it looks like. You can find out for yourself at Desmos.com for all your graphing calculator needs. This value, don't forget that this is the original function. The original function evaluated at negative 3. That's negative 3 plus 3 to the 2/3. I like 0. All right. One more. Gotta throw in some. Gotta throw in some trig, right? Okay, here we go. First derivative. Derivative of sine is cosine. Derivative of cosine is minus sine. We set the first derivative equal to 0, or find where it does not exist. Find our critical numbers. Let's go ahead and add sine to both sides. If the sine of x is equal to the cosine of x, then it must be x is pi over 4, because in the first quadrant, they're both positive, or the third quadrant, 5 pi over 4, they're both negative. It's the only time they're both equal. If you had if the squares were equal, it'd be all 4 quadrants. But we have to make sure they're both positive or both negative in this case. Now, I'm going to assume an interval of 0 to 2 pi, but we'll kind of talk about how we could do this in general as well. So I'll maybe make it go further, but let's talk about it. This will be 0. This will be 2 pi. This is pi over 4. 5 pi over 4. Yeah, so I'd have to, we'd have to think about how to do this in general. That's why I think it'd probably have a restricted domain for us. Something smaller than pi over 4 are test points, right? We need some test points. I'm going to use a test point of pi over 6. I'm going to use a test point of pi. And I'm going to use a test point of, let's go for it, 11 pi over 6. Remember, in our test points, we want to, I'm going to just write up these intervals really quick. That is a 4. Let me make it, that's still not clear. 5 pi over 4. And 5 pi over 4 to 2 pi. There we go. Our test values now. We're going to evaluate our first derivative. So I want k at pi over 6. At pi over 6, we're in the first quadrant. Ugh, it matters. And since it matters, boop, boop. Oh, good. It didn't show anything fancy. Let's go ahead and just evaluate it. I'm not using the graphing functions features here. That'd be cheating. But we can check our mode, make sure we're in radian mode. Fantastic. And quit. Thank you. Now we can just evaluate. You know what? Here's what I'm going to do. It's on video, so I could kind of be lazy. Cosine of x. Right? I'm evaluating the derivative 3 times. Cosine of x minus sine of x. That's what our derivative is. Oh, no. No, no, no. I'm sorry. I would totally edit that if I was an edit kind of person. Let's do this instead. Let's do pi divided by 6 and store that for x. Now, anytime I type x, it's going to give me pi over 6. So now I could just do cosine of x, close a parenthesis, minus sine of x. I don't have to define any functions or anything like that. And it's going to give me a value that blah, 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 blah. It's positive. Next, we're going to do 2 store for x. 2? Really? Why would I store 2? How about pi? Pi, store for x. Yeah, I know. 3 of you probably jumped on that right away. You're right. Now I'm going to do second enter and then second enter again, and then I don't have to type it again. As -1. But really all we care about is that the derivative at pi is negative. So we have increasing and we have decreasing. At pi over 6, at pi over 6, we will have pi divided by 6, store for x. And we'll bring it back one more time. Can you guess? I bet it's positive. Look, the same number as when we use the positive pi over 6 as well. So this is positive. And we are increasing again. So we know a ton of information. We know that we are increasing from 0 to pi over 4. And again, from 5 pi over 4 to 2 pi. We know we are decreasing from pi over 4 to 5 pi over 4. We also know that we have a maximum and a minimum. In particular, our pi over 4 is going to give us a well, let's see. We can find out if it's relative or absolute. Let's evaluate first. Let's find k of pi over 4. Original function. Sine of pi over 4 is square root of 2 over 2 plus cosine of pi over 4 is square root of 2 over 2. That's 2 square roots of 2 over 2, also known as square root of 2. So one of our points is pi over 4, comma, square root of 2. Remember, exact value, that's a 4, not a 9. We'll find k of 5 pi over 4. We find that actually k of 5 pi over 4 is the same value. Remember, this is in quadrant 3. It's where sine and cosine are the same value. If they're the same value, we have two of the same value, but they're two negative ones. So we'll have a 5 pi over 4, comma, negative square root of 2. If we want to know, since we have a closed interval that I defined like after I started the problem, if we want to know if this is an absolute max or min, we really do need to evaluate at the endpoints as well, right? It's that whole, what view of the graph are we taking, what snapshot? At 0, sine is 0, cosine is 1. So that's a point 0, comma 1. These are all points. At 2 pi, sine is 0, cosine is 1. So that's a point 0, comma 1. What I know is that the square root of 1 is equal to 1, so the square root of 2 must be bigger. And we have our maximum, and we have our minimum. And because we know the values, we know that these are absolute maximums and absolute minimum. And that is a very long and drawn out set of examples to help you out with the first derivative test and extra practice. Yeah, I know you were right in that last set of notes. Let me scroll back down. There you go. Now hit pause. Thanks for watching, guys. I hope to be back in the classroom soon.